In life, there are two types of charges. We call them positive charges and negative charges. We'll find out that calling them like this makes certain equations convenient for us, which is nice. As we know, all matter is made up of atoms, and atoms are neutrally charged if everything's all nice and stable. What do we mean by neutrally charged? For every amount of positive charge that's a part of the atom, there exists an equal amount of negative charge. Positive charge exists in the nucleus of the atom in the form of a bunch of protons glued together with a bunch of neutrons. Each proton has a charge of positive E, where E is called the fundamental charge. We'll define E more precisely later, and also this E has nothing to do with Euler's number, which you may have seen before. It's an unfortunate fact of doing physics that there are often more variables we'd like to define than there are letters of the alphabets, so sometimes one letter has to mean two different things. Anyway, each neutron has a charge of 0, which may be why they're called neutrons. They're neutral. Negative charge exists outside the nucleus in the form of a bunch of electrons, and each electron has a charge of negative E, where E is again the fundamental charge. So if you have a good old normal everyday atom, it's neutral if it has the same number of protons as it does electrons. In the Bohr model of the atom, electrons orbit the nucleus at some constant radius, but we now know thanks to quantum mechanics that electrons don't actually do that. Instead, they exist in a sort of electron cloud that probabilistically determines where you're likely to find the electron, but that goes into a whole lot more complicated stuff that we'll talk about maybe some other day. Even the animation I have on the screen here doesn't accurately convey what's really going on. For some problems that are thrown at you outside of PEEP physics, you might have to assume that electrons actually do orbit the nucleus, even though we know for a fact that this isn't how electrons actually behave. Usually this involves considering a centripetal force and somehow relating that to the electron's movement. Anyway, moving on, sometimes things are not so stable, and you can end up with atoms that lose electrons or gain electrons. If an atom gains electrons, we say that it's not really an atom anymore. It's now an ion. A negatively charged ion. Why is it negatively charged? Well, it has more electrons than protons, so some of the electron charge is cancelled out by the proton charge, but the rest of the electrons have nothing to cancel them out. These extra electrons make up the net charge of the ion. If an atom loses electrons, we say that it's also not really an atom anymore. It's now a positively charged ion. Why is it positively charged? Because some of the protons in the nucleus cancel out the charge from all of the electrons, and you're left with some remaining or extra protons that have a total positive charge. These protons make up the net charge of the ion. Now you might be wondering, well, what if we take away the protons? Couldn't we ionize atoms that way? Well, I guess you could take away the protons from an atom, but actually the number of protons in an atom is what defines the element it is. So if you remove protons from an atom, you're fundamentally changing what element it is. You're not even looking at the same thing. Despite that, maybe there still might be some way you could make it electrically charged. Now we should probably talk about why we even care about positive or negative charge in the first place. Positive charges repel other positive charges, but are attracted to negative charges. Negative charges repel other negative charges, but are attracted to positive charges. In electricity, opposites attract. Now you might be wondering, well, if like charges really do repel, then what's keeping the nucleus full of protons together? Wouldn't every nucleus want to just explode because of all the repulsion between the protons? Well, you're right that electrically the protons do repel each other, but there's actually another force at play here, and it's called the strong nuclear force. It only noticeably acts over teeny tiny distances, on the order of femtometers, distances that are impossible to see in day-to-day life, but not impossible to imagine at the scale of an atom. At that scale, it's a much stronger force than the repulsive electric force the protons feel. So as a result, unless you can separate the protons more than a few femtometers, they stay close to each other mostly due to this other mysterious force. But now what about this? If the electrons really are attracted to the protons in the nucleus, then what's keeping them from flying into the nucleus and neutralizing it? Well, this one is a trickier one to answer. The way the Bohr model tries to handle this is it agrees, yes, the electrons are attracted to the protons, but that doesn't mean that the electrons have to fly into the nucleus. The Bohr model says that if you have electrons that are already circling around, they're constantly attracted to the nucleus, and that attraction is what's keeping them in orbit. The same way the moon being attracted to the Earth keeps it in orbit around the Earth. But we already know that the Bohr model is wrong, don't we? And the argument we've made here is still quite flawed. So you'll have to wait until quantum mechanics if you want any seemingly more accurate representation of the phenomenon, even if it is more difficult to understand. One more important thing to discuss, if you define a system and no charge flows into or out of that system, then the total amount of charge in the system will never change. Interestingly enough, human beings have yet to find a case where this property doesn't hold. These charges can interact any way they want to, but as long as no charges enter or exit the system, the total charge in the system is conserved. We call this important property the conservation of charge. Now, all matter is made up of atoms, so not only can you have individual atoms which become ions, or atoms that are ionized, but also you can have entire objects that become electrified, or electrically charged, because they contain some amount of positive ions or some amount of negative ions. Now we have positively charged and negatively charged objects, not just ions, that are attracted to other oppositely charged objects and repelled by other like-charged objects.
Let's eat! Oops!